Okay, so last time we started into chemistry, which was really a science that it became a science in the 18th century. In the days of Galileo and Newton, there were people fooling around with chemical reactions and trying to do experiments and so on, and they discovered some practical knowledge, but they didn't have really any understanding of the subject yet. And the old Greek views of the basic elements being earth, water, air, fire, those views were still very influential. And so people did not have any understanding of what was happening in the chemical changes they saw, and that didn't start until the guys that we started to talk about last time, Black and Priestley and Cavendish. Now, one of the really important discoveries that would lead to chemistry developing into a science that made sense was Priestley's discovery of oxygen. And remember what he did. He took a rusted metal, it was actually mercury in his case, and he had this huge magnifying glass that he would shine on it, and he found basically that he could in effect burn the rust off, okay? Or, he could make pure mercury again. And when he did that, a gas came off the metal. And lo and behold, this gas had these wonderful properties that it burned really, really vigorously. And it was very breathable. It would keep a mouse alive for a long, long period of time, longer than ordinary air. So he realized that what he had done by intensely heating this rusted mercury was he had gotten the burnable and breathable part of air out of this mercury. Now we could do the exact same thing with this. If you took Priestley's magnifying glass now, and we shined it on this rusted steel wool here, and heated it up really intensely, one of the things that would happen is you would start seeing this water level go down. It would get that there would be a gas that would come off of this rusted metal, and that would be the gas that Priestley discovered. So now, unfortunately, Priestley did not correctly interpret the results of his own experiment. He didn't think that what he had done was, in effect, liberated gas. At the time, people had a certain view of what was taking place in combustion when you burn something. And their idea was that when something, it released something into the air. Okay, so a burning process was the fire substance being released into the air. Now, that is not so this is there something wrong? Oh. So the let me see. I think I actually may have misspoke just then. Yeah, no, that's right. So the for instance, if you have a candle burning, they thought that that was releasing this fire substance into the air. Well, of course, they were bothered a little bit by the fact that if you have a candle burning in a closed vessel of air, that that it used up some of the volume of air actually decreases, right? We saw that. The water level rises. Okay, so it seemed to them, well, we're adding this fire substance to the air, and the volume is going down. So that seemed kind of weird that you would add something to the air and the volume would go down. But they said, well, it's a strange property of this fire substance, but, you know, what the heck. And then they discovered even something more peculiar, which was that in this case of, well, in the case where metals rust, see, they actually thought that the metals were, again, they were liberating this this fire substance. And so they couldn't figure out why the metal actually gained weight in this process. And they actually started thinking, well, maybe this fire substance has negative weight. So the theoretical ideas at the time were all confused. And they had everything backwards. So even though they were doing the right experiments and they were making some really important discoveries, they didn't understand those discoveries yet. And the guy I'm going to get to talking about today, Antoine Lavoisier, he was the first one who actually understood all these experiments that people had been doing. Now, the last experiment that we covered last time by Cavendish, remember, was a really key experiment. Remember, Cavendish dissolved acid. I mean, he poured acid into metal. Like if you have metal filings, and you can use lots of different metals, but iron will certainly work. If you have iron filings and you pour sulfuric acid into them, well, a gas bubbles off, and a very light gas. And so Cavendish did that, and he discovered this new gas. Okay. Now, this gas was so light that he thought it might be this fire substance that everybody had been talking about. Okay. So he had the idea of adding this gas to the gas that that comes off when you heat the rusted metal. Okay, and he thought that by adding these two gases, he would restore, he would get normal air again. That's what he actually expected to get. Well, what did he get, Daniel?
Water.
He got water, right? Because what he was actually, what Lavoisier would explain, is that he was actually adding hydrogen and oxygen, and he ended up getting water, but he expected to get air. Okay, so that's how screwed up the. I mean, there was no understanding yet of what was going on and how to interpret these experiments. They were doing crucial experiments and discovering these gases, but like I say, there wasn't there wasn't yet an understanding of what was going on. And the guy who did develop the first correct theory and turn chemistry into a real science is the guy I want to tell you about today. And his years are 1743 to 1794. And Lavoisier made a couple of, he laid down a couple of very, very important principles by which these questions in chemistry could be sorted out. The first thing he did, he offered a definition of what it meant to be a chemical element. Now, at the time, remember I've told you there's been a lot of loose talk about, you know, the elements being earth, air, water, fire. But, you know, what did that exactly did that mean? Obviously, people realized that not everything was literally made of dirt. In other words, what is earth? What did they mean by that? Does that mean solid substances are somehow all made of dirt? Obviously not. They were a little loose about what exactly was this element, earth, and whether it actually existed in pure form anywhere, and how could you tell that you had pure earth? So there was no clear way to distinguish elements from compounds, and they weren't even given any very precise definitions. Well, Lavoisier says if we're going to have a real science, I mean like Newton had with physics, we better be careful about the way we use our terms and have objective ways of deciding whether something is an element or a compound. So he offers this definition of an element. This is worth writing down. An element is a pure substance that cannot be decomposed by any chemical process. Okay, so what does he mean by a pure substance? Well, it means it's not a, it's not a mixture of different things. You didn't take a bag of salt and a bag of sugar and mix them together. It's the same stuff throughout. Okay, but being the same stuff throughout obviously isn't a strong enough criteria for an element. We have to add something to that. And what Lavoisier adds is there is no known chemical process that will decompose this material. That you can't take this pure substance and by any known process at all create two other substances. Okay? Now, what's the importance of him adding this qualification? Can't be decomposed by any chemical process. What if you what if you had the biggest hammer in the universe and you were able to smash this stuff with unbelievable force, and that created some change in it? Okay, now Lavoisier is ruling that out, and he's saying, well, there may be processes that chemists don't know anything about right now, but we're doing chemistry, and I'm defining what a chemical element is. And what we're interested in is substances that can't be broken down by any chemical process, that are the last stage of analysis in chemistry. Now, whether or not there's some crazy processes that, physicists might discover someday that might be able to break down these chemical elements, that doesn't change the fact that they're chemical elements. Okay, now this was crucial because it made the concept of element something that meant something specific to chemists. Okay, and by the way, physicists eventually would figure out how to decompose these chemical elements, but it would be a long time in the future. But Lavoisier's definition was exactly what was needed to make the idea of element precise and something that scientists could actually deal with. Now, he still needs something here. He needs some way of knowing. I mean, let's say you have a pure substance. You operate on it by some chemical means, do some chemistry experiments, and you turn it into two other substances. Now, does that necessarily prove that the first substance wasn't an element? Well, I mean, you have to be careful here in distinguishing between what are elements and what are compounds. Now, if this is our definition of an element, what would a compound be? Well, yeah.
Many elements combined?
Yeah, I mean, it's a pure substance, but it is composed of elements. Now, we need an objective criteria for deciding between elements and compounds. Can you think of what that should be? I mean, if you've got, let me see. I mean, basically what you need, I mean, what Lavoisier figured out was you can do it with a mass balance. That the key principle here is that matter is conserved. That you should have any chemical reaction that you have. So let's say you've got A, and you add some chemical B to it, and it ends up going into, two other compounds, C and D. Well, the mass of A plus B the mass of reactants, say, has to equal the mass of the products. So Lavoisier now can make more precise what he means by decomposing a a chemical, some substance. He says if you can take substance A, say, add heat, whatever you do to it, and turn it into, say, B plus C, but and verify that the mass of A equals the mass of B plus the mass of C. Then A is a compound, is not an element. Right? You've broken it down, and you've shown that, well, A really has gone, there's nothing missing here. It really has gone into B and C because the masses add up. And, if substance A can go into two other substances that together weigh the same, then you really have broken A down. And you know what you've broken it into. You've broken it into B and C because the masses add up and there's nothing missing. So this was a key principle that made chemistry into a quantitative science where they could actually, they could weigh the reactants and the products, make sure that nothing had escaped, that they had accounted for all the mass, and whenever they saw something like this, of one substance going into two others that together weighed the same, they knew they had broken it down. And whenever they had a substance that they had done lots of experiments with but never managed to break down, that they call an element. Okay, so Daniel.
Did they ever try breaking something up, and occasionally you would have something break into three masses?
Oh yeah, definitely. You can. Some of the. They had. There are common metal ores that consist of the metal, and carbon and oxygen. Okay, so they would, and you can, through processes that they discovered, they figured out how to break, to analyze into that ore into all three components. Okay, now you can see Lavoisier is on a good track here. He's not just he's not approaching the subject in this speculative way that the Greeks did, and then the people in the Middle Ages that decided that everything was mercury and sulfur and salt. He's not just spewing out guesses like that. He's laying out precise definitions and then laying out a procedure by which you can actually decide what is an element and what is a compound. Okay, now one of the things that one of the bad ideas that people had that had stopped progress in chemistry was this idea that even when you had an element, the elements could transmute and turn into other elements. See, that's Lavoisier's view is the elements stay the same. All they can do is combine with other elements to form compounds. But you never lose an element. You know, it's conservation of elements. Now, but people had arguments against that, going all the way back to ancient Greece. For example, if you take a potted plant, okay, and let's say you carefully weigh the soil that you start with, and then you have this little plant in there, and you water it. Maybe you even keep track of exactly how much you water it, how much weight of water you put into it, okay? Well, the plant starts growing. You know, maybe it grows into a big tree. Now, where did the tree come from? People asked. All you've done is add water. Now, did the water turn into a tree? Daniel, you're shaking your head. Where do you think the tree came from?
It had to come from something that grew from life or from age and from nutrients. It had to have been like a seed or something.
Okay, but you figure it's taking its material out of the soil?
Yeah.
But actually, if you weigh the soil beforehand, okay, soil plus tree, okay, you weigh it beforehand. I mean, when the tree's real small. And then, 2 years later, okay, after the tree's gotten big, you weigh it again, soil plus tree. Well, it's gained in weight quite a bit. Now, what's the only thing you've added is water, people say. So somehow water has become wood. Yeah, Troy.
Also all the air around it.
Yeah, that's a good thought. Maybe it's taken something from the air. Well, that's what Lavoisier thought. He didn't believe for a second that water had miraculously transformed into wood. He thought that, but he stuck to his conservation of mass principle and thought, well, it's probably getting something from the air. Now, they would eventually figure out what it was getting from the air. In fact, I gave you a hint, actually, last class. Troy?
The carbon dioxide.
Exactly. Remember that the last time, the very first new gas that people discovered, it was discovered by Black, who I told you about last time. He figured out that plants really liked this new gas that he had created, this carbon dioxide. Well, that's exactly what's happened. There's a very small amount of carbon dioxide in the air, and plants take that in, and that is what enables them to grow. But this issue of that chemicals could somehow undergo some change that would change them into completely different chemicals was still around back then. And this is one of the ideas that Lavoisier had to get rid of, had to refute, before he could really put chemistry on a solid foundation. And so what he did, one of Lavoisier's very first experiments was he took not the plant case that I just told you about, but another case that was similar. People had noticed that if you took water and boiled it in a glass container, that it would leave a little residue behind. Have you ever seen this? where you can take a perfectly clean piece of glass and perfectly pure water, okay, and you boil it. You boil the water away, say, and it leaves, a little bit of like white chalky residue in the glass. Well, people had noticed this, and they had said, well, somehow this heating process has caused some of the water to change into this solid residue that's left behind. Lavoisier said, no, water doesn't change into this white chalky substance. That would ruin his whole approach to chemistry if that happened. So he has to prove that doesn't happen. So he takes a glass container and he heats up the water in it, takes pure water, okay, distilled water, heats it in this glass container for 100 days. I mean, Lavoisier is a really patient guy. And he wants to create as much of this white residue stuff that people have seen as he can. So he keeps heating this thing for 100 days. And and then he when he's done, he separates the water and the white chalk in his glass container, and he weighs them. And he compares them to the original weights. What do you think he finds? Well, yeah, but what? How are the? So he's got. So let's put this. Let me see. Let's call this the water. Well, I'm gonna be telling you about a number of experiments that Lavoisier did. So you can call this section experiments. And number one, say water residue experiment. Now, so at the outset, he's got what he's got is glass plus water, and of course he adds heat for 100 days, and he gets glass plus water plus residue. And of course, what people had said before Lavoisier is that somehow some of this water has magically turned into this residue. Now, what Lavoisier finds with his really careful, accurate weighings is that he recovers the same amount of water he had originally. Weighs the same. Okay, so if we're balancing masses here, well, this water, the weight of the water is the same. So that cancels out. So now we've got glass. His original glass has gone to glass plus residue. Sure enough, that's exactly what he finds. He finds that the glass at the end of this experiment weighs less than it did at the beginning. And it weighs less by the exact weight of this residue that he finds. So what's happened? Yeah, I mean, what happened was when you take water and you heat it up in this glass for a long period of time, it actually dissolves some minerals out of the glass. Okay, so this residue, it wasn't that water was turning into this residue. It was that there were certain minerals that were in the glass that the hot water can dissolve out of the glass if you give them enough if you give it enough time. And so that was what was going on. The glass actually weighs less by the amount of the residue at the end of the experiment. So here Lavoisier has shown that you really can apply, this quantitative technique, using these carefully weighing the masses to figure out exactly what happened and to show that these miraculous changes that people had thought take place don't in fact take place. Water is water. Okay. Now, one of the other things that Lavoisier began to do, he knew about the experiments of Priestley, and so he was interested in investigating what was going on when things burned. Yeah, Troy.
Did he also know about Cavendish or not?
I don't think that at this early stage he knew yet about Cavendish's work. But Priestley did, and then he heard about it from Priestley a little later. Cavendish was a strange guy. He was very reclusive, and he actually didn't publish nearly as much as he should have. So he did a lot of things that people didn't hear about until years later. Okay, one of the things that Lavoisier does at this point is he does a little variation on the candle experiment. Actually, it was the sort of experiment that Priestley had already done. I think I told you that one of the things Priestley did was he took a glass vessel that had a little shelf in it, and he put a little sulfur there, and with the bottom of the vessel with water, submerged in water, he would heat it up with his magnifying glass, that sulfur, and it would burn. And then he would see the water level rise up. So that's just a variation on the candle experiment. When the candle burns in there, the water level rises up a certain amount. Well, Lavoisier does that same experiment with phosphorus and with one other variation, which you can guess. He very carefully weighs, the phosphorus beforehand, and then after it burns, at the end of the experiment, he weighs it again. And lo and behold, he finds out that the phosphorus, would you expect the phosphorus at the end to weigh more or less than it did at the beginning? Less.
Because it burned away.
Yeah. Okay. That's the way people thought about it. It burns away. It releases this fire stuff, whatever the heck it is, and so it should weigh less. Now, the only thing that bothered him about that idea was, what happens to the water level in the container? Okay, so the water level goes up, which means there's less air in the container, right? After you've burned. Where'd it go?
Well, it's burning up the part of the air that burns, and whatever part of it, whatever you're burning up, is taking some of the place of it, and it's taking up the other space.
Okay, but when you say it's burning up, keep Lavoisier's principle in mind here. Nothing ever disappears. Okay. I mean, it sounds like a really obvious principle if you state it this way, that, matter is, and it just sticks around. It can move places, it can change form maybe, but it can't appear and disappear. I mean, it's a simple principle that Lavoisier has got here, but it has amazing implications. Now, this is the case in point. Daniel at first thinks, well, okay, you're burning the phosphorus, so it has to be, it's burning away, right? So it has to decrease in weight. But we have this strange phenomenon that as the phosphorus burns, the air is disappearing. So where did it go? Now, if you look at it from Lavoisier's point of view, okay, conservation of matter, right? If the air is disappearing, well, it's all you're doing something to the phosphorus, and the air is disappearing. Lavoisier thinks, well, that air went into the phosphorus. The phosphorus should weigh more, not less. Had to have, right? Sure enough, that's exactly what he finds. Okay, so you take, so this is the experiment where he burns phosphorus in closed container. Okay, what he finds is when he burns the phosphorus, 20% of the air is, let's say, used up. Okay, so the volume of air decreases by 20%. And sure enough, he finds that the weight of the burned phosphorus it weighs more by exactly the weight of that 20% of the air that disappeared. Okay, so we will continue this afternoon, but you can see Lavoisier is making progress here.